Yeah, go ahead.
So, welcome participants. So, on behalf of Tamilnadu Science Forum and Popular Science Lecture Group, I extend my warm welcome to you all. Today, we are going to have a webinar on James Webb Space Telescope, popularly called JWST. This lecture shall be delivered by Dr. Varun Balerao, Associate Professor, IIT Bombay. We have with us two pillars of PSL, Dr. TRG and Dr. Jam. This meeting shall be in English, and we would like to have a brief introduction about Tamilnadu Science Forum and the speaker. This is the program schedule of this webinar. Let us first start with Dr. Sedaraman, who is going to introduce the TNSF, followed by the introduction of the speaker, Dr. Varun Balerao, by Dr. TRG. Dr. Varun shall speak about 40 to 45 minutes, and we will have a question answer section about 30 to 45 minutes. Vote of thanks by Kumar, our EC member, our joint secretary. We will try to wind up the event before 6 p.m. This is our schedule. PSL, with regard to the PSL is part of Tamilnadu Science Forum and started functioning from 2018 onwards, although TNSF is functioning from 1980 onwards. PSL came into existence when we decided to strengthen the activities of TNSF in a higher science area. We have conducted 45 lectures so far, and this is our 46th lecture. The first lecture was held in July 2018 as a Stephen Hawkins Memorial Lecture. PSL used to have its lecture in the hall. Particularly, we used to have it in the Anna Centenary Library, and it adapted to virtual meetings during the pandemic period. We hope that we may have a few more virtual meetings in the pandemic. Still, the pandemic is over. Some of the participants are shown by the device name. We request them to change their name by right-clicking the icon, so that if you are raising the question, we can address your name. We will mute all the mics except the speaker and request all of you to raise your hand when you have a question. The question answer section start, we will unmute the mic and those who wish to ask the questions to the speaker. We would like to get the feedback on this webinar from you, and we are going to post a Google form in the chat box. The link is for this is going to be provided in the chat window. Please fill up the form by providing your contact details and your opinion of this program. We'll keep in contact. We will keep your contact details as confidential, and that will be used for communicating our future programs only. In the meantime, we have also a Telegram group meant for PSL. To join the Telegram group, click the link provided in the chat window as well. You can also send email popular-science-lecture plus subscribe at googlegroups.com to become a member of our Google group. You will get a notification of our program on your mobile through Telegram. Since the registrations are heavy for this event, we are unable to accommodate all those in the meeting. We follow the first come first serve basis principle. We are broadcasting this lecture in the YouTube. If any of you dropped from this meeting due to any reason and unable to get back to the meeting, we recommend you to go through the YouTube broadcast. The link is going to be provided in the chat box. Save this link separately, which may be helpful for you in case if you are dropped out of the Zoom. So with this, let me hand over the mic to Dr. Sedaraman to introduce Tamilnadu Science Forum. Sedaraman, please.
Sedaraman is not here, Vijay.
Oh, he's not available. Yeah, I think Dr. TRG will cover the introduction of TNSF as well, because he is a founder member as well.
Thank you very much, Vijay.
Yeah.
And all our friends. I'm very happy to talk about, initially for a few minutes, about Tamilnadu Science Forum. Tamilnadu Science Forum was started in 1981 when we were all graduate students in Madras University, and several of us put together our efforts and started. And this has grown to a very big institution now, with the participation from all sides, young and senior people, etc. And it has also taken up varied directions. Now, major things like school education, science education, primary school education, middle school, etc. And literacy program was one of our strong points earlier. And this was going on for several years. And we decided that we should also focus on higher level sciences. And that is one of the reasons that PSL group was also started, which has been functioning for the past 2 years, 3 years now. Now, Tamilnadu Science Forum has various wings, which talks about health issues, which talks about women's issues, which talks about even the current COVID situation in a big way. And it has spread, and it is also running children's science magazine like Tulir, and also middle level or elementary level science education in English on Jantar Mantar, various things of this kind. So we have our brochures available, and Vijayan will make it available as soon as if anyone needs. So you can ask him through the chat box for the details of Science Forum in a big way. Now, PSL has been running for the past 2 years with several lectures. I was also the first person to give the first lecture, but those days it was given in public. It was held in Anna Centenary Library, and also held in Institute of Mathematical Sciences. It was also held in IIT Madras or Madras University. In several other places we have held this program. And now for the past 2 years, after the COVID, we are forced to go for online, which has been fairly successful. Our topics are very, very varied. And every year during Nobel Prizes, we always have lectures on Nobel Prize winners in every subject. And this has been a fairly successful program, and we want to carry this forward. So with this, I'm going to start introducing the speaker, Dr. Varun Balerao. First of all, I should thank him for accepting to give this talk on this Webb telescope, which we are all looking forward to hearing from him. Varun actually did his BTech in electrical engineering from IIT Bombay. And then he moved to Caltech, California Institute of Technology, for a PhD program. And during his thesis, he worked on NuSTAR. It's essentially focusing hard X-ray telescope. It's very interesting that like the way we focus our optical conventional thing, you can also focus X-rays and other thing. And we can try to find out what is happening at the center of the galaxy, what is supermassive black holes, what are the various things which are exciting about neutron stars. So the universe is full of surprises for us, waiting for us to learn from that. And we are now talking not in terms of mythological times like few thousand years, we are talking in terms of billions of years of the origin of the universe. So it's a really exciting thing to talk about universe at after some 300 million years or 400 million years. So that is the time when galaxies were getting formed and various other things were becoming start acting. And some of these experiments that we can do such experiments is really exciting. And this telescope, which is going to be launched, which is launched already, and it has also reached the so-called Lagrange point recently, is also a success of this program. And people are excited about what is it that's going to tell us about the universe and the to a lot of knowledge which we are going to gain from here. Now, Varun is originally associated with the NuSTAR program, and also he was a winner of this Vaidya Rai Chowdhury postdoctoral fellow at IUCAA, Inter-University Center for Astronomy and Astrophysics. And he did a lot of interesting things about AstroSat, the multi-wavelength space telescope. At IIT Bombay, he has the STAR lab, which is associated. His group works on the development of Growth India, India's first fully robotic telescope. It's very exciting areas, and we are all looking forward to what they are going to achieve. And he's the recipient of the Vainu Bappa Gold Medal. the highest honor by Astronomical Society of India. He is also associate to the Indian Academy of Sciences, DST Inspire Fellow, and he's been awarded IIT Bombay Early Research Achiever Award and Kirti Ramamridam Award for Creative Engineering. And normally I visit IIT Bombay almost twice or thrice a year when the things were under control. And we used to, it was always interesting to meet people like Varun and others in IIT Bombay. And we are looking forward to learn more things about the galaxies, supermassive black holes, and neutron stars, and gravitational waves, etc. Now over to Varun to start giving his talk. He will give for about 45 to 50 minutes, following which questions can be asked. As Vijayan suggested, you can put your questions even now as you go along in the chat box, and Vijayan probably will take up those questions one by one. But if you want to ask directly, you can also do with after taking permission from Vijayan and the organizers by raising your hand. They will allow you to unmute and then you can ask the question. Now, Varun, it's up to you.
Thank you very much, and a very good afternoon to everyone. We are all here together on a Sunday afternoon. Everyone excited to hear about the James Webb Space Telescopes. It's great to be with all of you here. It would have been nicer if this was an in-person event. Of course, we could have met and interacted. But I think this online forum does give us a chance to reach out to a larger audience who may not have been able to come and meet at a specific place. So as was introduced, I have built astronomical instrumentation. So I built telescopes as part of teams that built NewStar, AstroSat, Growth India, and so on. And that is the approach that I'm taking towards the James Webb Space Telescope as well. So this is what we are going to talk about today. Of course, Sunday afternoon, 4 o'clock is probably a time when usually we would probably want to be sleeping. So in case you want to quickly run off and sleep, here's a one-slide summary of my entire talk. Okay, so what is JWST? Well, the James Webb Space Telescope is a large infrared space telescope that is orbiting L2 at a large distance from the Earth, and it will help us study the earliest galaxies, the evolution of galaxies, birth of stars, and to look for building blocks of life in planets around other stars. So that's the summary of my talk. Okay, maybe we can just close here. Any questions? Okay, I'm getting messages from the organizers saying I should not close here and maybe go into a bit more detail. So for those who are not already fallen asleep from this, let's actually break down this sentence step by step and look at all of these details. Okay, so the first part that we should look at is a telescope. So as astronomers, why do we really care about telescopes? And this takes us back some 400-500 years, okay, to these two gentlemen. This was an era in Europe where technology was just starting to make progress, and there was this concept called spy glasses, which were likely invented by this person, Hans Lippershey. Okay, so this guy, what he did was he was making small telescopes, which were called spy glasses, and they were gaining a lot of popularity all around Europe. And this person on the left, Galileo Galilei, is one who's more famous and associated with telescopes. What he did was that he took the design and improved it. So Galileo's friends actually convinced their king not to buy one of these imported telescopes and go to our own guy Galileo, and he can make something better for us. And Galileo, of course, did. And this is Galileo's telescope, or a replica of it. You can see pictures here. This is on one of an old book published in 1656, where Galileo is using the telescope to point out things in the sky. And Galileo himself was probably not the inventor of the telescope, nor was he probably the first person to point it to the sky. But what he did was that he took it in a very precise manner. He made good telescopes. He studied the sky very methodically and very scientifically. And for that time, Galileo's telescope was actually a masterpiece. Usually when normal people talking about telescopes, we talk about magnification. So let's talk about Galileo's telescope in that aspect. Professional astronomers usually don't care a lot about magnification. But so Galileo's telescope was a big deal for that time because it actually had 30 times zoom, and that's awesome. So what did he do with that? Well, he pointed it to the moon, and the first observations that he did was that the moon was not a smooth, perfect sphere, and this was a big deal for that time. Okay, today we know there are mountains and plains and plateaus and everything on the moon, but in that time and that generation, being told that the moon was not a perfect sphere, as had been said in many books thus far, was actually a shocking revelation. It was like saying, Rajnikant is not actually superhuman. Why would you do something like that? But not just that, he actually used the telescope to study many other things. He actually found that the sun is not perfect either, and it has spots. And then he looked at Venus, and he showed that Venus actually has phases just like the moon. So just as you can see a crescent moon or a gibbous moon or a half moon, you can actually see phases on Venus as well with a telescope. He found that Jupiter has its own moons. Again, a big deal thing. There were, for the first time, there were objects that were seen going around something else. Okay, this was a time when we thought that we were the center of everything. And then he also had a discovery of bumps on Saturn. Now, wait a minute. Up till now, I was saying Galileo is great on Saturn business. Well, this telescope was a crude handmade device, not the best quality. So Saturn, as we now know, has nice rings around it. But with Galileo's telescope, he did not have sharp enough images to actually realize that they were rings. So instead of seeing a planet with a ring around it, he just saw something that seems to have protrusions on two sides. So he called them bumps. Okay, so where do we go from there? So that's telescope. We've been using them for several centuries now to look at the sky, but just telescopes is no longer enough, right? These days, we always want to go for large telescopes. And the reason that we go for large telescopes is that, well, larger is better, right? I mean, everyone wants a large house, large car. So why not have a large telescope? We can show off nicely with that. Is that really why we would go after larger telescopes, or is there going to be some distinct advantage that we can get from that? So let's try to put things in perspective, right? This is about 37 millimeters, just under 4 centimeters was Galileo's telescope. The telescope itself was larger. That does not matter. What we are talking about is the size of the lens. Today, if you go and buy a basic telescope, okay, something that you'll get in the market today, those are often called 3-inch refractors. So in a telescope, the typical diagram that we have all seen in school, for instance, has one lens here, and then we take the tube, look through it. This front lens is called the aperture. Okay, and it's very similar to the terminology used in cameras. So those of you who are into photography, you always talk about camera apertures. Okay, so the aperture, the main lens, has a diameter of 3 inches. That's quite a common size. As I was an astronomy enthusiast, I had a larger telescope. See, I'm showing off with larger here, and that was about this size. So the main lens was 6 inches, but wait a minute, instead of refractor, I'm saying reflector here. So what does that mean? I actually had a telescope that had a curved mirror instead of having a lens, and that also can help in focusing light. Okay, so this is nice, but then we have graduated since then. You heard about the Growth India telescope in my introduction. So here's my 6-inch reflector, and let's put it in perspective next to the Growth India telescope, which is among the smaller professional telescopes. So this is what the telescope looks like. The main mirror sits here, and that is 70 centimeters across. Okay, so my 6-inch reflector is here in that scale, and Galileo's telescope would be about the size of this laser pointer that you are seeing on screen. This is the beautiful Mount Saraswati, and you can see the Growth India dome over here. So nice place to visit. Now, Growth India is not a very large telescope by research standards, but why do we still want these large telescopes? So here's a very simple demonstration, something which we have all played around with. The advantage with larger is clearly shown here. Okay, so this guy is holding up a lens in the sun, and while the sun, we do feel hot in direct sunlight, what the lens is doing is that it is taking all of the sunlight falling on all of that area and bringing it down to a single point. And that is really important. What is being done is light which would have spread over such a large area is now getting focused at a single point. And that focused single point means that if you put a detector there or if you put your eye there, don't do that with the sun, but you are going to get all of that light. So going from Growth India telescope to the world's largest telescopes, here is a full list. This telescope here is going to be about 30 meters in size. So Growth India is not actually that. Growth India on the same scale is that small dot you see now. So India is actually a partner in this 30-meter telescope. India has some partnership in this as well. The largest telescope in the country right now is about this size, 3.6 meters. That's in near Nainital. And the star of today's show here, of course, is James Webb Space Telescope. Okay, so down here you see a bunch of space telescopes, and James Webb is the largest of all of them. The reason why we are going for that is that a larger mirror will collect more light, so it will let us see things that are fainter. But that too is not the only reason why we want to go large. Okay, so I'm going to show you, this is a picture taken from my house, and in this picture, down here, there's a little bird sitting, okay, and this is the bird. This is a white-breasted kingfisher, if I am not mistaking the name. I'm bad with these, okay, but you don't believe me? Let me just zoom in this photo and show you the bird. So this is the black box here. Let me zoom in on that. And there it is. You see the bird here? This is exactly like this one, right? Come on, I've magnified the image. You don't trust me here? So why is it that even after zooming, this bird and this speck thing here does not look like each other at all? That has to do with the intrinsic property of a lens itself. So it's called resolution. Resolution, or in crude words, we could think of it as sharpness, tells you what is the smallest detail that you can see with a telescope. Now, my phone's camera has a very small lens over here. The lens is only a few millimeters across, and that is not good enough to actually make out this bird. So how do I know this bird was sitting there? This is a picture of the internet, by the way. This is not what I saw, but what I saw was actually this. So now you can see that they look a bit more similar. You can see this is a kingfisher. You can see the beak properly and the head and so on. And the way I now got this photo is actually by using binoculars. So I took binoculars, and here is an unzoomed version of the same photo. So you can see this filmy style, nice circle around it. And with binoculars, what changed was that instead of having a lens that was a few millimeters, now I had a 7 or a 10 centimeter lens. And that gives me much better resolution. So even if I do a lot of zooming in like this, the image quality cannot improve by just zooming in. You need a larger lens or a larger mirror that will actually give you sharper and sharper images. So that is the other reason that we really want to go after large telescopes. Okay, so larger aperture means you get better resolution or more clarity, more sharpness in your images. That, of course, if you're looking, trying to study a galaxy, if you're trying to find planets around other stars, you really want to be able to make out small details. Okay, so that takes us to the second point, large. But what about this? Why are we talking about infrared? Now, infrared is something that we usually associate with as heat vision. Okay, so but let me explain it a little bit. We have a mixed background. So for some of you, this might be quite easy. So what's shown here is different types of electromagnetic radiation. Okay, so radio waves, microwaves like the kind you have in microwave ovens, visible light, X-rays, gamma rays, they are all form of light, and they come in what are called electromagnetic waves. You can think of waves in terms of their frequency or in terms of their wavelength. So visible light has wavelength of the order of half a micrometer or half a micron. So millimeter is 1,000th of a meter. As all of you know, micron is 1,000th of that. Infrared is a bit longer. Radio waves can be up to kilometers in length. Okay, so when you are talking about radio waves, we are talking about longer wavelengths, shorter and shorter as we go here. X-rays and gamma rays are actually smaller than atomic nuclei. So this row here shows you different objects of the characteristic scale of that type of light. But you can also think of it in terms of frequency. For example, if you are listening to FM radio, frequencies are around 100 megahertz. So that would be about 10 raised to 8. Okay, so this is the region in which you have radio waves. Optical light has much higher frequencies, and X-rays, gamma rays, even higher frequencies. So what we are going to study with the James Webb Space Telescope is this part, the infrared band. Infrared is what we usually associate with heat vision. So here's a set of pictures. They are the same scene. This image is taken by me. This is me with this camera over here, looking at our own image on a screen. And the same thing on the right is taken with an infrared camera. And you can see that you can make out enough similarities in these images. You can see my cap, but you can also start seeing other things. You can see that my skin is much warmer than my cap. Or on the other hand, you have a person here with this white hat, and in the infrared image, you can figure out where his head is actually touching his hat, because those parts are warmer. And some other amusing part, this woman's glasses, for example, are cool in infrared, whereas red is hotter. So you can see that her face is actually hotter than the glasses or the scarf that she is wearing. So every time we use a new wavelength, so you also heard about NuSTAR in my introduction, and NuSTAR is an X-ray telescope. So we want to examine all of the astronomical objects with different wavelengths, because each wavelength gives us a different perspective. We could not have figured out, for example, that there is actually a head inside this unless we saw the heat signature of that head. But infrared also has something else to offer. So here's a picture, again, same scene in two wavelengths. The color coding on the right side is different. So when we take infrared images, you and I can't see infrared. So what we have to do there is that we actually take what are called representative color images. Okay, so then in this image, the colder parts were shown in blue, going through green, yellow, and so on up to red and white, which is the hottest. Whereas here, red and black are cool things, and then white and yellow are hotter things. You can see that in optical light, this is a fireman trying to go into a room, and there's a lot of smoke in that room, so he can't see anything. But on the other hand, if you use infrared camera, you can see that there's a person lying here on the floor trying to protect himself or herself from the smoke, and infrared can very clearly see through that. So if we are looking at, say, the birthplace of stars, there's a cloud of gas and the stars are being formed inside that. In optical light, we won't see any of that. But with infrared light, we can see right through that dust. And that is why we want to do infrared observation. There's a third reason for infrared as well, and that has to do with something called redshift. Now, some of you may have heard about a phrase called Doppler effect. And a common example that we get is when you hear a train rush by. Okay, as the train is coming towards you, the whistle of the train sounds higher frequency, and then as it goes away from you, the frequency becomes lower. Any kid who is imitating a car goes by knows this intuitively. They'll make a sound which starts off as a high pitch and then suddenly switch to a lower pitch. The same thing happens with light as well. If an object is coming towards you at very high speeds, its frequency will appear higher, its wavelength will appear shorter, it will appear bluer as compared to visible light. On the other hand, if some, say, yellow object is moving away from you, the wavelength will become longer, frequency will go lower, and that will appear as red shifted. But what I'm talking about here is a slightly different effect. This is called cosmological redshift. Okay, so what I have on screen here is that we have Earth, and I have a galaxy over here, and this galaxy is very far away, so far away that light had to travel 4 billion years to reach us from that galaxy. Okay, which means that when the light left that galaxy, the universe was a different place. The galaxy itself was not how it is today. I have no idea what that galaxy is like today. Okay, the universe, as you know, you will have heard about something called the Big Bang. So the universe was born about 13.8 billion years ago as a massive explosion. At that point, everything was in a single place, and it has been expanding ever since. So if we rewind time by 4 billion years, the galaxy was probably closer to Earth, right? Quite definitely closer to Earth. The entire universe is expanding. So now, suppose the galaxy emitted a photon at that point, and let's call it a green photon. So I have given it a wavelength of 500 nanometers. So to remember the scale again, meter, 1,000th of a meter is a millimeter, 1,000th of that is a micrometer or micron, and 1,000 times smaller than that is a nanometer. So this is 500 nanometer green light. This was emitted by that galaxy 4 billion years ago. Then as the universe expanded, that light photon was traveling towards us, but everything is growing. The universe itself is expanding. So that light wave is also getting stretched. So 2 billion years ago, there are complicated equations and integrals that you can do for this, but the answer I'll tell you in a nutshell. About 2 billion years ago, the universe between this snapshot 4 billion years ago and this snapshot 2 billion years ago, the universe had grown about 17% in size, which means that the wavelength of this light, instead of being 500 nanometers, is now 17% longer, and it becomes yellow light. And then if we fast forward all the way to today, when the light is just reaching Earth, between 4 billion years ago and now, the universe has expanded by about 35%. So this light, instead of appearing green light, which is what the source emitted, will appear red to us. Okay, hence the word redshift. Okay, that's all great, but where is the light? What kind of light are we looking for? So if you look at stars, okay, typical emission from stars is either in UV or ultraviolet light. There's optical, there is infrared. It depends on the temperature of the star. The sun emits in peaks mainly in optical. That's at about 6,000 degrees Kelvin, 5,500 degrees Celsius. Stars which are much heavier than the sun, 20 times, 30 times heavier than the sun, they actually peak in ultraviolet. Whereas stars which are much lighter than the sun, say half a solar mass, they will peak in infrared. All right. And then the universe itself is opaque below 91 nanometers at shorter wavelengths. What does that mean? Light actually interacts with matter, and the universe is primarily made of hydrogen. The Big Bang created mainly hydrogen. So there's a lot of hydrogen around. Space is not pure vacuum. Space is largely empty, but it is not completely empty. There are all these few atoms floating around per cubic meter. So in a typical house room, there would probably be 100 atoms, okay, if we had the same level of vacuum as space. Some places are even less dense than that, but the universe is huge. So for a light ray that has been traveling for billions and billions of years, it will interact with some atom along the way. And if your wavelength is shorter than about 91 nanometers, then the photon is energetic enough that it can ionize hydrogen, and that means hydrogen completely absorbs it. So you can't see anything below this wavelength in a typical volume of the universe. So you want to look at light when it is being emitted from the source has to be of wavelengths longer than this wavelength, typically. There are some exceptions, but we won't go into technical details. Okay, so suppose I have this light at 91 nanometers, also given as 910 angstroms. Okay, that is ultraviolet when it is being emitted. But I want to look at very far, far away galaxies. And here I'm introducing a term called redshift. So in the previous slide, we talked about this concept. As things are going away, they are actually appearing redder and redder. This is quantified by some term called redshift. So higher the redshift of an object, the farther away it is. And that also means that the light left it that much time ago. So we are seeing things on that object not as they are today, but as they were billions and billions of years ago. So at a redshift of 20, which is what James Webb Space Telescope actually wants to target, the wavelength of that light will be about 1.9 micrometers. Okay. On the other hand, if you take our green light again, 500 nanometers, which is 5,000 angstroms, at redshift 20, that becomes light of 10.5 microns. So these are all wavelengths which are longer than what the human eye can see. 1.2 microns, by the way, is something that your cell phone can see. So try this. If you have, say, a TV remote, okay, sometimes you may see a red light on your TV remote, but it is largely emitting IR. And your phone camera, if you point it to it to get better night mode photos in your phone, it actually is cheating. It is taking some IR light and then painting it as optical. And you can see these IR remotes and IR diodes and so on with your phone. Okay. So James Webb Space Telescope, then to cover this entire range and then some, it actually has a functional range of about 0.6 microns. That is red light that you and I can see, going all the way to 28.5 microns. Okay, so that is, in astronomy parlance, we call it the near infrared and the mid infrared band. So that's the range in which James Webb Space Telescope is going to work. Okay, so that's enough about infrared. What next? So it's a space telescope. So I want to study infrared grade, and I showed you a lot of these different large mirrors and large telescopes on Earth. Why are we putting James Webb Space Telescope in space? Well, the name is Space Telescope. It would be quite lame if we called it Space Telescope and put it on the ground. But as it turns out, that is not reason enough to launch something in space. We need something more concrete than that. Well, here are a few reasons. The first is that most of this wavelength range is actually blocked by the atmosphere. Around 10 microns, maybe some light reaches the ground, but at longer wavelengths and so on, the atmosphere simply absorbs a lot of infrared light. Atmosphere absorbing light may seem strange, but if you really look around, the atmosphere in a large city also absorbs optical light. You can't see very far away because there's a lot of smoke and dust in the atmosphere. So your horizon that you can see is barely a few kilometers. Now, if you look at the full height of the atmosphere, it blocks a lot of light coming in. So to study certain wavelengths, we have to go to space. One place where this blocking of light is great for us is that the atmosphere actually blocks all the UV and the X-rays and gamma rays coming from the sun. Okay, so some of you may remember that about 10 years ago, there was this large discussion about the ozone hole, and the ozone layer was getting depleted. Fortunately, a lot of that has been fixed quite a bit by now. So it's great for life on Earth that it's being blocked, but not great if we want to study in those wavelengths. So that's why we need to go outside the atmosphere. We need to go into space. But there is other problems with the atmosphere. Okay, so we have all seen and heard in school that stars twinkle. So what is twinkling? Okay, so this is a series of images taken with a very high speed camera. I'm going to show this again in a moment. And then they were slowed down by a factor of 10. Okay, this is with a 4.2 meter telescope. So this is what a very zoomed in image of a star from the ground looks like. Now you can see that within this image, there are a lot of small blobs. There's a blob here, there's a blob here, another blob here, another blob here. That is actually the sharpness of that telescope. This is how good the image of the star could have been if William Herschel telescope was actually in space. But on the ground, what happens is that the sky is extremely turbulent. This is not very different from, say, looking over a fire. So if you are sitting around a bonfire on a cold night, or if you are cooking something and you look over the pot, you'll see things appear wavy. So here we have tens of kilometers of air above us, and all of that is turbulent. It's moving due to winds and everything, and that makes images move. So what happens is that due to the atmosphere, this image completely jumps around and you get this giant blurred blob instead of, so this is twinkling, or in technical jargon we call it seeing, which is a funny name if you think of it. And that means that there are extreme limitations on the quality of data from the ground. There are some modern techniques like adaptive optics which allow us to correct for this, but largely it is still a big pain in the neck to work through all of that. It would be much easier if we can just go out beyond the atmosphere. That has used for a lot of different things. So space telescopes have been used for a while. Astrosat, what you see here, is India's very own space telescope. It was launched about 6 years ago. I am fortunate enough to have been a part of the team that built this. I was working on this instrument called cadmium zinc telluride imager. You'll notice that this doesn't look like our conventional idea of a telescope. This actually has 5 different types of telescopes on it. So these boxes here study the sky in medium energy X-rays. This studies the sky in hard X-rays, soft X-rays at lower energies. There's a UV telescope, optical telescope, and then there is a scanning sky monitor. So all of these telescopes here are pointing up here, studying some source up here, whereas this thing sitting on the side is actually studying the rest of the sky. So this is India's very own space telescope. It has been giving great results. You can find more details at this website, or if you look up Astrosat Science Support Cell, you can find details there as well. So we launched telescopes in space to get rid of this pesky atmosphere and the problem that it introduces. It of course means that we can't send observers with it. So everything is going to be recorded by cameras and then transmitted to Earth. And we will analyze that data sitting in the comfort of our homes or offices where we have an atmosphere to breathe in. Okay, so space telescope it is, but not just space telescope. We also said that we want to put it at something called L2 at a large distance from Earth. So what is this L2 business now? Okay, The question that we usually need to address here is space cold? We usually think of space as cold, and you may have heard of things like in deep space, the average temperature is minus 270 degrees Celsius, or just about 3 Kelvin. But that is if you're far away from sources of heat. Okay, if you think of why does the Earth have an average temperature of a few degrees Celsius? So the Earth is really maintaining this temperature because of all the heat that we are getting from the sun. There is some internal heat, all the lava that we have inside is cooling, but the dominant thing is really heat from the sun. Okay, and now if you are a satellite in orbit around Earth, low Earth orbit can be pretty hot. Okay, so the next thing that we are doing, our group at IIT Bombay, working with a lot of different institutes, TIFR, IUCAA, RRI, PRL, and ISRO centers, and so on, we have proposed a mission called Daksha. Okay, it's a next generation set of space telescopes that will study explosive high energy X-ray, gamma ray events, explosions all throughout the cosmos. Daksha is going to be 10 times better than any other telescope that has been flown by NASA, ESA, you name it, 10 times better than all of them. But that's not the subject here. What I'm showing here is simulations and calculations that we have done for the performance of Daksha. And this is an early thing saying that if we did not do any special thermal engineering, we just launched the satellite, what would the temperatures on the satellite be? So some parts of the satellite would get as hot as 78 degrees Celsius, whereas others would get as cold as 18 degrees Celsius. That's still not very cold. Okay. Now, the problem with these temperatures is that all of us, you, me, everyone, is also emitting light. We don't see it as optical light, but in infrared we do. Remember when I showed you those images of heat vision? There was no infrared light that was being shown there. We were just detecting the heat coming from the person. This is something that in the pandemic has actually become a regular experience for us. If you're going into a mall or some other establishment, they point a temperature gun at you. What that does is actually it is measuring the infrared radiation coming from your hand. Okay, so this is right in the wavelength range that James Webb Space Telescope wants to study, and that is a problem. If you are using, say, an optical telescope to look at stars, you don't want to do that in, say, a cricket stadium with floodlights on. You want to go to a very, very dark place. Okay, so let's understand this problem again. The Earth's temperature gets heavily regulated by our atmosphere, so the moon is a better reference. So the moon, if I have sunlight shining from this side, this surface of the moon can get as hot as about 130 degrees Celsius. Whereas this side, which is away from the sun, there's no atmosphere to efficiently carry the heat around. So this side can go as low as minus 170 Celsius. That's a huge change. You don't want to be in direct sunlight. You want to work at much colder temperatures, because at this temperature, it would emit a lot less heat, and heat is infrared light. Okay, so in low Earth orbit, we have to worry about heat from the Earth and heat from the sun. If we go far from Earth, at least we can get rid of this pesky little problem. So we now have to worry just about heat from the sun. And in order to get rid of that as well, we can simply block the sunlight. You wear a cap. So that is exactly what James Webb does. So here is this point called L2. So what is shown here is this is the sun. And the size of the sun and Earth and orbits are not to scale here. This is the Earth, moon is going around the Earth. Okay, so why is the Earth going around the sun? So the sun's gravity is pulling the Earth in, and then there is centrifugal force that is pushing it out, or you can think of it as gravity providing centripetal force. I won't go into the pedagogical arguments. I'm going to call it centrifugal force. So gravity is countering the centrifugal force, and that is keeping the Earth in its orbit. Now, if I take a point over here, okay, this L2 point, what I have is that the gravity of Earth will pull objects in this way. The gravity of the sun will also pull them this way, but there is higher centrifugal force now because you're further away from the sun, moving a bit faster. So these effects completely cancel out, and this becomes a stable point. There are 5 such stable points. They are called Lagrange or Lagrangian points. L1 is in between. Here the centrifugal force is outward, Earth's gravity is outward, and sun's gravity is inward, and so on. So these are, it can be mathematically shown that there are 5 stable points, and L2 is the place where we have put James Webb. Now L2 has an advantage, a bunch of advantages. First is that an object at L2 also takes 1 year to go around the sun. So here's an animation of James Webb's orbit. You see the moon going around the Earth. James Webb is not sitting at L2, it is also going around L2, again for a bunch of complicated orbital dynamics reasons. We don't need to worry about those. The point though is that if we pause this animation right here, okay, let's go back and restart it. And let's pause it over here. Okay, so as you can see, there's a telescope here and there is this kite-shaped structure. But from the telescope's vantage point, the sun and earth are very close to each other as seen from the telescope. That means that a single cap can completely, or this sun shield can completely block out the earth and the sun. It also proves to be an advantage that it completes one orbit around the sun in 1 year. So it means that it is in a relatively fixed part of the sky, night sky for us, makes it easier to communicate to the telescope, to send commands, get data. And that is why we have launched it at L2. There are other telescopes that have been put in similar orbits, WMAP, Gaia, and so on. So this is not the first telescope that went there. So why are we capping out the sun? Let's get an idea of relative fluxes. Flux is a technical term for brightness with some other units taken care of. Okay, so everything, as I said, sun, earth is emitting infrared. The telescope itself, if it is at room temperature, will emit infrared and it will be blinded out by its own light. Okay, how bright are these things? So what we want to study with James Webb Space Telescope, let's say there's a distant galaxy and we use a unit called Jansky to measure brightness. This is named after Carl Jansky, who is the father of radio astronomy. And NJY here means nano Jansky. Just as a nanometer is a billionth of a meter, a nano Jansky is a billionth of a Jansky. For those of you who want to know the technical details, this is the specifications under which this is calculated. So the faintest galaxies that James Webb Space Telescope will see will be 9 in some units called nanojanskis. For comparison, suppose I was operating the James Webb Telescope and I am standing, let's say, at a distance of 1 meter from it, then my brightness will be 190 million billion nanojanskis. Okay, so I will be a factor of this much brighter than what that galaxy is trying to see. So it is literally like trying to see a candle in front of the sun, except that the candle itself is a billion times brighter than what we are trying to see. So it is more like seeing a single atom emit while being dominated by all of sunlight or something like that. On the other hand, the sun itself or the earth, so we go far away from earth, great. So I am now far away, that problem is solved, but the earth is still emitting and the earth is huge. Okay, that means that the earth's radiation reaching there is also huge. It is about 10,000 billion nanojanskis or simply 10 kilojanskis. Okay, so these things really have to be blocked out. We need to put in that sun shield, and that is a brilliant technological solution that had been thought out. So what is done here is we have something called a sun shield. I'll show you more pictures in a bit. What you are seeing here, what looks like aluminum foil or the kind of gift wrapping shiny paper that you use, it's actually not very different from that. This is a kind of plastic sheet which has been coated with aluminum and some doped silicon and some special materials. And there are 5 of these sheets. So you see here 1, 2, 3, 4, and the 5th one is under this. And these 5 sheets together actually are blocking out the sunlight. Okay, so what happens is that you have the telescope is always oriented like this. You have the sun shield on one side, you have sunlight coming in, it always hits the lowermost shield here, and that layer can get pretty hot. Okay, the peak temperature over there can go to 125 degrees Celsius. If that sounds very hot, remember that's the same temperature we talked about the moon as well. But then this heat is absorbed and re-emitted from this side and re-emitted here. Then there's a second layer blocking that, there's a third layer. And all of that combination together means that the inner layer is extremely cold. The coldest point on the inner layer is actually at a temperature of minus 235 Celsius. That is fantastic. Why not put just a single shield? Well, this is like if you go to a cold place, then instead of taking one thick blanket, actually 2 thin blankets do a better job. Or if you ever have accidentally or intentionally broken open a vacuum thermos bottle, you'll notice that it always has 2 layers. So multiple layers actually work much, much better. And vacuum is a great insulator. There's no air in between. What these zigzags here are showing is that heat here is actually getting reflected out. So from here, it would come out reflected between these surfaces and would eventually leave from this side. Okay, so the net effect that you get is that the innermost layers are kept extremely cool, and that is the temperature at which we want to operate the telescope. Now the sunshield here, this image does not do justice to it. So here's a full size of that sunshield, and this now starts giving you an idea of how huge this thing is. Okay, so here's a person, here are 2 more people in between. They usually say this is size of a tennis court. Okay, I'm not a tennis person, so I'll give you the area of this. This is about 1500 square feet. Okay, that's the size of a large house. That's the area of each of these layers of the sunshield. Okay, this is about the size of 3 badminton courts, for example. Okay, so let's recap now and let's come to James Webb itself quickly. So what are the challenges that we have to do? Well, we want to take a big telescope, fit it inside a rocket, take it all the way to L2, then make it cool. And of course, it has to be robust, reliable. We can't go there and fix it if something goes wrong. So here is James Webb itself. You saw this a little bit. This is the mirror. The mirror itself is 6.5 meters in diameter, but is not a circle. Instead, it is a set of hexagons. And that is because each of these smaller hexagons is easier to make, and they can actually be folded in for launch. And I'll show you that in a moment. These are the sun shields. Here you have some star sensors. You have solar panels over here. You have this antenna for communicating with Earth. And at the back here are all the instruments. We'll look at all of this in more detail. Here's James Webb for scale. This is a tennis court. This is a 3-story high building, 3 floors. That's how large the telescope is. Here are those individual mirrors. You'll notice that the mirrors are not silver, they're golden in color. And that's because it doesn't matter what they look like to us, but gold is a much better reflector in infrared. The mirrors themselves are made of beryllium, extremely lightweight. You want to keep things as light as possible when you're launching it in space, because launching is expensive. So here is the telescope in all of its glory, all of its beauty. This is for an environmental test. On the ground, they had this giant chamber where they created the cold of space. And now you notice that the mirror looks odd here. Okay, in these shots over here, you don't see the full hexagon anymore. And the reason for that is these 3 segments and these 3 segments have actually been folded in on the side. And the reason for that is that the telescope has to fit inside the rocket for launch. Okay, so let's look at this rocket now. So we are going up the lift onto the top of the rocket. The rocket itself is about as tall as a 15-floor building. So that's slowly we are going up. This is just to get a scale of how big these things are. And despite that, it is not large enough to take the telescope. So here is the telescope itself now, finally sitting at the top. You can see that this is very closely folded in. Here's the telescope being brought in. You see the 3 mirrors on the side, the main mirrors here, and all of the integration and everything is being done by people wearing clean room suits. So you don't want any dust to stray in there. That can cause problems. And here's the rocket cap finally fitting in. By the way, this seems small, but remember this itself, the inside of that rocket, that nose cone or the fairing as it is called, that's about 150 square feet. I'm in Mumbai, that is the size of a small house in Mumbai typically. So these things are huge. And then of course, you can't talk about a space telescope before looking at launch videos. So here is launch main engine. After 7 seconds, the boosters will ignite. There it is. Fantastic liftoff. This happened a couple of months ago, just less than 2 months ago. Ariane 5 is extremely reliable. This is launched from a site around the equator, European launch vehicle. Extremely reliable rocket. They have done more than 100 launches so far. And there it is, Webb off to study the universe. Some of you may have seen this. What you're about to see here is this is actually a camera on the launcher itself. So the rocket stages, they fall off. Finally, the last stage of the rocket had a camera. There are some things that you may or may not notice here. You see hexagons over here. These are the side mirrors that have been folded in. You'll soon see this again. This is the antenna that is used for communicating with the Earth. And this became popular as the last farewell view of the James Webb Space Telescope. I'll show you more views of it later. So this wasn't the last one. But here it is released from the rocket. And you can see the Earth's reflection here, and that's gone. Now you can see the Earth itself. Soon you will see reflection of jets. That there it is, the jets firing to maintain a separation between the two. All of this had to be timed and choreographed very carefully. You don't want the mirror to directly point to the sun ever. As soon as this is separated, until now, the satellite, the rocket was providing power. So now we have to deploy the solar panels immediately to start generating power on the telescope to keep it active. So soon you will see the solar panels getting deployed. You can see more rocket firings here as a reflection as the rocket is steering now to keep this in the camera field. Down here is beautiful Horn of Africa. And right about now, you are going to see the solar panels deploy. Let me forward this a bit. So there it is, solar panels slowly opening. And with those solar panels, now the satellite will start generating its own power. The telescope will start generating its own power. And with that, the dependence on the charge in the battery is no longer held. So this was great. Solar panels deployed successfully. The purpose of this camera, by the way, is not just pretty pictures. They actually want to verify that all steps are going correctly before taking the next steps in the sequence. So there it is, a farewell from James Webb as it headed off. And what did Webb do after that? Well, the telescope, this is the final shape, but it was not launched in this way. It was launched folded up like this. And 31 minutes later, after launch, you saw the solar panels deploying. About 2 hours after launch, you had the high gain antenna deploy. I pointed out that to you. And now this folded up thing, which was sitting inside the nose cone of that rocket, slowly starts opening up. So first we have the sun shields, which are unfolding. After those two things came out, the telescope itself was lifted up clear from the sun shield. This is a momentum flap details, which I won't go into, but now the cover around the sun shield is opening, as you can see here. And then this shield was stretched into place. So just as you have your bent sticks which hold a kite in place in shape, over here there are wires which are pulling this tight. So it's not very different from a kite. You will also notice that there are these kind of markings over this. These are rip stops. So if somewhere in space, suppose a small micrometeorite or something hits this, you don't want the entire thing to get ripped up. So there are these fused layers and sewn layers in between. And then here's the main secondary mirror coming in. So the way this telescope will work is that light will come in, get reflected from the main mirror into this mirror and back into the center, which is where all these instruments sit. And now about 2 weeks after launch, finally the telescope is in its final shape. And you can see here that the sun shield is always pointing sunward, and the telescope is open to observe the rest of the sky. Okay, so that is James Webb deployment sequence. What else is going to happen? Well, after all of this, the telescope now has to cool down, and cooling down takes a lot of time. You will have noticed this. It is much easier if you have something at room temperature, and if you pull out something from the fridge, you put it in a microwave oven or on your gas stove, and within 5 minutes your cold soup will have become hot soup. But you take the same boiling hot soup, you keep it in the fridge for 5 minutes, it does not go all the way to that cold temperature. So cooling is always harder. You are just radiating heat. Removing heat is difficult, so it will cool down, take a lot of time doing that. About a month after launch, which happened a few days ago, one of the instrument called the near infrared camera, or NIRCam, actually started operating. This is when the temperature of the telescope had gone to about 120 Kelvin. That's about minus 150 degrees Celsius. And after that, this step is what has just been completed. This is called the initial optics checkout. So those mirrors were all deployed and they were shaken up during launch and so on. They all have to be aligned perfectly to function like a single large mirror. And that alignment has to happen at nanometers level. So we are talking about the maximum tolerable misalignment in the mirror is 10,000 times thinner than a human hair. And there are 132 small motors, actuators, which are adjusting all those mirrors to make sure that that is happening perfectly. Okay, and this focusing and realigning those mirrors is what is going on right now. About another month from now, the temperature will drop to about 40 Kelvin, that's minus 230 degrees Celsius. Telescope alignment is going on. Then after about 4 months, when after the telescope itself has cooled, there is another instrument called the mid-infrared imager, MIRI, and MIRI, actually, even the operating temperature of the telescope, which we saw was going to be around 40 Kelvin, is not going to be cold enough. So it has another unit on it called a cryocooler. So think of it as its own personal refrigerator, and that will take it to 7 Kelvin. Okay, Kelvin is a different scale. Absolute zero is the lowest temperature that is theoretically possible. That is 0 Kelvin. That's minus 273 degrees Celsius. So this is very close to that, minus 265 or so degrees Celsius. And then they are going to calibrate the telescope, point it at stars, look at the images. The first pointing actually has been done this week. And after the calibration and everything is done, finally about 6 months after, they'll also track moving targets. The James Webb is going to be used to study, for example, the moons of Uranus are a big deal. And Uranus moves as compared to the background star. So you have to be able to track that. There's also another asteroid impact mission called DART that is going to try to deflect an asteroid, and that's happening. JWST will also be trying to track that. So all of this will go on for a total of 6 months, after which the scientific operations of the telescope will begin. And now I promised you I'll show you the telescope again. So this is specially for you. This is the first time anyone is seeing these two movies here. What you are seeing is images from the Growth India telescope on the left. All these dots here are stars. And you can see in a box here, there's a star that is rushing from left to right. This was data we took specially for you for the purpose of this. So we took Growth India telescope and we used it to observe the James Webb Space Telescope. And here you can see it moving. Remember, it was orbiting around L2. At the same time, we also reached out to our colleagues in Taiwan, and they took a movie here. And you can see the telescope moving. They actually observed it for a longer time. These two are taken at the same time. But if you look carefully, you will notice that the stars in the two images are not the same at all. They are very different backgrounds. And that is because the stars at a very large distance. So just as if you hold a finger in front of you, you close one eye, the finger appears here. You close the other eye, the finger appears here. That's called parallax. So what we are seeing here is the parallax of James Webb Space Telescope. And we will be taking more data like this. And in another couple of weeks, we will share some more exciting images and movies. So that's the story of James Webb Space Telescope. What we would talk about next is science to be done with the telescope. But I am actually going to ask the organizers here, should I go on for another 10 minutes or so covering some of the science cases, or should we pause here for questions?
No. You go ahead.
All right, so let's talk about what science we will do. Right, so we have gone to L2, large distance from Earth, but we now want to study something, right? We haven't done this just for fun. So what do we want to study? We want to study the earliest galaxies, the evolution of galaxies, birth of stars, and we want to look for life on other planets. That's all amazing. How do we do this? Well, there are 4 telescopes that are going to be used to do this. There is NIRSPEC, Near Infrared Spectrograph. FGS is the fine guidance sensor. Then there is NIRCam, Near Infrared Camera, and there is MIRI, the Mid Infrared Imager. And these have 3 types of units in them. There are spectrographs, so think of them as prisms. They'll take the light, spread it out, and it will help us study these things. There are different kind of images that are present there, and there's something really cool called a coronagraph. We'll come to all of that. These instruments, remember, this is the sunward side. You can see solar panels here. The instruments are all situated at the back here, right behind the primary mirror. Light goes in through this hole over here. And you can see this is NIRSPEC, this is MIRI, and these are the other instruments at the center. They're all quite large in size. And the way that they will work together is how we will be able to address these four goals. So we want to search for the first galaxies formed in the early universe, and then we want to study how those galaxies actually evolve. This is quite insane, right? We are used to thinking of the sun and earth as things which are just always been there. But the universe was born 13.8 billion years ago. There was nothing but hydrogen gas, a little bit of helium, maybe trace amounts of lithium, beryllium. That's it. Now, if you look around, there are a lot of other elements that you see. The laptops that or mobiles that you are using this, seeing this lecture on, the key component there is silicon. The key component for our life, carbon, oxygen, nitrogen, all of these were not a part of the universe when the universe was born. So we also want to study how these were formed, how the elements got recycled, and then we want to look for life around other planets. Okay, how will we study these deep galaxies? So the image that you are seeing in the background here is the Hubble Ultra Deep Field. So what scientists did was we took the Hubble Space Telescope and pointed out it at a blank part of the sky where there are no bright objects, and they observed it for 10 days, and that gave this amazing images. And every little dot that you see here is actually a galaxy. Some of them are nearby, so you can see beautiful spirals here, and there are elliptical galaxies here. And if you look carefully, you'll also see things like merging galaxies and so on. But this went up to a redshift of about 10 or a bit further. With James Webb, we will be able to go even further. We will be able to study galaxies when the universe was a few percent of its current age, when the first galaxies were being formed. So we'll take these very, very deep surveys, and from those images, we will be able to understand the formation of galaxies. And then not just formation, by looking at galaxies at different wavelengths and at different distances from us. Remember, the further away we are looking, light had been traveling longer. So we are looking at the universe as it was back then, not how it is right now. So by looking at galaxies which are 13 billion light years away, and then 10 billion light years away, and 5 billion light years away, we will actually see how galaxies are changing over time, and how the chemical elements are distributed in these galaxies. And galaxies collide. The universe is a very, very, very violent place. All sorts of insane things happen. Our own galaxy very likely has cobbled up a bunch of galaxies around it. And there is evidence that we see in terms of streamers as these galaxies were torn apart as they fell into our galaxy and so on. And we'll be able to study all of this by the help of these cameras. How do star systems form? So there's usually a giant cloud of gas and dust, and it starts coming in under its own gravity. And then that gas and dust cloud collapses and forms stars, and suddenly the pressure rises enough to start nuclear fusion. So at the core of the sun, it's like billions of hydrogen bombs going off continuously to generate all of that heat. So how exactly does all of this? And in this process, why does there suddenly appear a disk around a star? How do planets form in that disk? How do stars evolve? How do they die? And this element recycling business here. So these stars, in the process of fusion in their course, that's where all the carbon and all the helium and all the gold that all of us like to hold is all getting manufactured there. But that's at the center of the star. So how is it getting distributed? So these heavy stars have to die. They have to explode at the end of their lives in supernovae. And with those, they have to spread that around. And we will be able to study how this process has been happening throughout the history of the universe. Okay. And then comes other interesting things. We now know thousands of planets around other stars. But are there any Earth-like planets? We know maybe 4 or 5 candidates of that sort by now, planets which may in principle support life. But from that, from being able to in principle support life to actually having life is a huge step. So can we actually find those blocks of building blocks of life there? Are there different types of exoplanets? Why are some planets like Earth rocky, or why are some comet like dominated by ice? Why are some things like say Jupiter and Saturn completely gas rich objects? So how do these things form? How do they evolve? And is our solar system something really unique? Are we special, or are there a lot of other solar systems which are just like that? And will there be life out there? I mentioned something called a coronagraph that I'll come to. So if you want to image a planet next to a star, that's very, very difficult. The Earth's brightness is a billion times less as compared to the sun, because the sun is emitting all of this light. The Earth is shining by reflecting a very tiny fraction of that light. So what you would want to do if you were an alien in a spaceship looking at that, you would hold your hand out to block the sun and then try to look at the earth after that, right? That drastically improves contrast. So coronagraph is a very high-tech way of doing that. So in the center here is a very, very, very bright star. Okay, and at the side here is an image of what is called a brown dwarf. So a larger sibling of, say, Jupiter. Now this star is 10,000 times brighter than the stray light that is appearing here. But all the light of the star has been very cleverly blocked by this thing called a coronagraph. So this is from a ground-based telescope called Keck-2 in Hawaii. But James Webb Space Telescope also has a bunch of coronagraphs like this, which will actually allow us to block that starlight and directly image and study these planets around those stars. And not just that, as this planet, so suppose this was a planet, this particular case is not, but suppose this was a planet that was orbiting around the star. Okay, if the system is like this, you would see the star in the center and the planet go around this way. But if it is edge on, the planet may pass in front of that star. And then we can do something amazing called transmission spectrum. So as the planet is passing in front of the star, if your resolution here is clear enough, you'll see that the planet is appearing as a black shadow, but there's a very faint atmosphere. So 99% of the star's light is coming directly to you. Light from this part, light from here, light from here, light from here is all coming to you. 1% of the light is just blocked by this planet. And 0.1% of the light is passing through the planet's atmosphere. Now the atmosphere, if it is an Earth-like planet, for example, the atmosphere will have oxygen, it will have carbon dioxide, it will have water, and all of these actually absorb very specific wavelengths of light. Okay, for example, the reason your microwave oven works is that microwaves are absorbed by water. And what is shown here is that if we look at the spectrum of such a thing, we will actually be able to detect these very, very tiny absorption bands. And that will tell us that there is carbon dioxide and there's methane, and some of these gases are very short-lived gases and they are very easily lost from an atmosphere. So the only way that these gases can exist in the atmosphere is if there is some process that is generating them. And for a few key molecules, they can't be generated by natural activity. They have to be generated by life. So these are called biomarkers, and James Webb Space Telescope will actually allow us to look for these biomarkers in planets around other stars. So that's the whole journey. That's the kind of stuff that we really want to study with this telescope. Last two slides now. Science is always an international collaborative effort. So we'll give you just one example of how we are collaborating. GIT is the Growth India telescope that I've talked about a couple of times. One of the targets for James Webb Space Telescope is this object called HD 80606b. Okay, and this object is actually a star and a brown dwarf, a Jupiter-like, not a brown dwarf, a Jupiter-like planet in a very eccentric orbit. So instead of a circular orbit, the orbit is like this. Okay, it's an elliptical orbit, which takes 114 days, but it passes very close to the star. So each of these, so these dots here show the orbit, and the small circles here are spaced at half-day intervals. Okay, and these, when it passes close to the star, in a period of just 6 hours, the surface temperature rises from 800 Kelvin, that is about 500 degrees Celsius, to 1500 Kelvin, something like 1300 degrees Celsius in just 6 hours. And that, what it does is that kind of flash heating actually sets a lot of turmoil in the atmosphere, and that will change the atmosphere and expose parts of the atmosphere that would not usually be seen. And what is planned by a group of our collaborators is that they're going to point JWST to this and study these effects to really understand the full composition of that atmosphere. But to do that, they need to know exactly when this close passage is going to happen. And to prepare for that, we actually undertook a campaign with a bunch of observatories around the world, including Growth India Telescope. So you see an image here, you see a few small white specks here, those are stars. There's a binary star here, and this in here is that star with the planet around it. So we took observations of that, looking for signs of this close passage. In fact, not particularly this, we were looking for signs when the planet passes in front of that star to get a very small dimming. So in all of these endeavors, science is always international. There is massive global collaboration that's always going on. I will end by pointing out to something called spin-offs. So when we develop an instrument like this is one of the finest pieces of engineering ever done by humanity. You may have heard scare stories like there are 340 single point failures. Each single thing has to go right. And we pulled it off, right? Humanity as a whole has pulled this off. And the technologies developed for this have a lot of everyday applications right now. The high precision, so James Webb Space Telescope, the work started in late 90s. Some of the high precision mirrors that had to be made, they developed very high speed optical sensors, high precision optical measurements, and you already actually benefit from them. So if you go for LASIK surgeries now, the modern surgeries can map out the cornea and the lens of your eye at a very high speed, and that has been done uh, based on technologies that were actually developed by those companies for James Webb Space Telescope. The new IR detectors that we get, the Mercator detectors and so on, were all originally developed for James Webb. Okay, so you can look at sites like this where it will tell you what innovations were done for this and how they have helped society as a whole. So I will end with that, leave a few URLs here if you want to get more details. Then there is a lot of content online. So these were what I thought would be most suitable. They're in slightly increasing order of technicalities. And let's break here for questions. Thank you, everyone.
Okay, thank you. Vijayan?
Yeah, we have a lot of questions.
Yeah.
The chat
So
box.
Okay.
you can slowly, but I'll just start with one question. Varun,
Yes.
when you are looking for potential possible life, like origins of life kind of question, the information you are getting is what might have happened some billions of years before, right? The
Yes.
actual information is. Are you expecting life at that time?
Okay, so James Webb, although it will be able to study things which are 13 billion years old, the life part of the question is going to happen for things within our Milky Way galaxy. And on the scale of the universe, the Milky Way is rather small. So at most, we are looking at things as they were thousands of years ago, or 10,000, 20,000 years ago. Okay, so for example, the distance from the center of the Milky Way to Earth is about 24,000 light years. So we are looking at, when we are looking at these planets around other stars, they have to be close enough so that we can actually resolve them. And we can separate out the star, block its light, study the planet. So we are looking for building blocks in our cosmic neighborhood, distances that are only on a cosmic scale, only thousands of light years as opposed to millions. So it is not that old. That said, we are looking for biomarkers. So we don't expect to get we don't expect to get photos of aliens waving at us or something like that. What we are going to do is we are going to look for signs of how intelligent life is a next question, right? We are just talking about life. So if there is a planet which has a lot of vegetation on it, then that vegetation does affect the chemical composition of the atmosphere of the planet, and those are the signs that we will be looking for.
Amino acids or organic material.
These are in James Webb studies, we are looking at atmospheric things. Organic stuff will not directly be present in the atmosphere. We will be able to see things like methane, carbon dioxide, changes in the water content, and stuff like that.
Okay. So Vijayan, you can probably post or go ahead.
Some people want to ask question directly. So I would advise them to raise their hand. What we can do is we can go one by one in the chat box. Simultaneously, we will also give turn for the people to talk to him directly. So what we can do is now we can answer a couple of questions from the chat box and we'll go for a direct answer. That way we can combine both.
Okay, so I've stopped screen sharing so that I can see who's raising hands. Should I call out to people directly, or Mr.
Yeah,
Vijayan,
you can start reading the chat box and start answering that question. So are you able to see that? Or otherwise?
Yeah.
Okay.
Okay, so let's see. There's a question from Ashika02 on YouTube. Okay, if actually, you know what, let's change this. If I start reading the questions, everyone is going to just be looking at my face as I'm reading questions. So Mr. Vijayan, if you could actually pick up the questions and then we ask them, that you can read the next question while I'm answering the previous one.
Correct. That way we can do.
Yes.
I'll start from the topmost question, then we'll go down and
Okay.
read it. After 3 or 4 questions, we'll go to the person who wants to talk to you directly. That way we
Okay.
can. Okay.
Sure.
Okay. Initially, we got a lot of questions from the YouTube viewers.
Okay.
So the first question is Ashika.
Mhm.
Whether BSc Physics candidate can enter into ISR?
Can BSc Physics candidates go into ISRO? Yes, of course they can. ISRO is a large agency which does a lot of different things. They need people who will, for example, build rockets. So they need mechanical engineers, they need electrical engineers, aeronautics, and so on. They also need managers. They need people doing office jobs. They need scientists who are going to do different science stuff with that. There is one common clarification that I would like to give here. Space science and astrophysics are two different disciplines. Okay, space science is very loosely, if I try to summarize it in one sentence, then I will say that space science is about putting stuff in space. Okay, so for example, if I am launching a satellite for showing you cable TV, that has nothing to do with astronomy. That's space science. On the other hand, the study of stars, planets, galaxies, universe, cosmology, all of that is astronomy and astrophysics. So I could do all of it from the ground. Galileo was doing it long before anyone even dreamt of going into space. Okay, so ISRO is a space science body. They have an astronomy group. There is a space astrophysics group in ISRO that actually does astrophysics from space, as the name suggests. But not all of ISRO does that. Okay, so if your interest is in astrophysics, maybe ISRO is not the only place that you go to. And there are various talks that you can look up online for career guidance for how to go into astrophysics. If you like space science, of course, yes, you can go to ISRO with that background.
Yeah, a lot of hand raise has been seen. Then let us go to the next question from the YouTube. Is how do it comes in revolution? Please tell how the apogee kick motor relating to it.
Sorry, can you read the question again? I didn't quite understand.
How do it comes in revolution? Come up. Please tell how apogee kick motor.
Okay. I'm not sure I understand the question. So let me try to first. Let me try to answer what I think I understand. So in an orbit, if an orbit is not circular, then there is a closest point in the orbit and a farthest point. The farthest point, if you are orbiting Earth, the name for Earth is geo. So apogee is the farthest point from Earth. Perigee is the closest point to Earth. And apogee motor is something that you would be using in doing orbit transfers. In case of JW, so for example, in case of Mangalyaan, or Chandrayaan missions, what was done is that it was first launched in the low Earth orbit, and then every time it was at perigee, you fire a motor to raise the orbit, so that starting from a first orbit like this, you then go into this orbit and then further and further, and then it went into a transfer. That was considered too high a risk for JWST, so it was directly launched onto a transfer orbit that would take it to L2. So there wasn't any orbit raising. There weren't any orbit raising stages in between.
The next question is what's our next galaxy from Earth?
The closest galaxy to Earth, the closest galaxy you would be able to see from India is or the easiest to see if you are at a reasonable site is Andromeda galaxy, but that is not the closest. It is the closest galaxy of comparable size to us. We actually have satellite galaxies that orbit the Milky Way galaxy. We have about 40-50 of them. There's the sculpted dwarf galaxy, there's large and small Magellanic clouds. You can actually see them from the southern parts of India in the right season with the right weather. Unfortunately, the right season comes out to be around monsoon, so getting the right weather is difficult.
Next question is Aditya L1 payload from ISRO also going to have shielding from the sun as it will be in L1 orbit?
Okay, so that's a great question. Aditya L1, the name itself has L1. So I showed you this diagram with 5 Lagrangian points. L1 is the point between the sun and Earth. Aditya L1, the name is Aditya. It is designed to study the sun. So we will not be blocking the sun from it. Okay, so but it is designed to withstand that heat, and it will not be working at these ultra cold temperatures and these far infrared wavelengths which were necessary. So to put it in context again, if you are trying to photograph something which is faint, and if you're looking for something faint and small, and if I come and shine a torch in your eyes, that is very, very annoying. But if you are studying the torch itself, then of course you have to shine it in your eyes. So you should not be hiding the sun if your purpose is to study the sun. So for that reason, Aditya L1 will not be having those kind of sun shields blocking their primary instruments.
The next question is from Janik Sengupta.
Mhm.
Could you please tell about the stability of Lagrangian point once more? How they are stable than other regions?
Okay, so imagine that I have the sun and I have something orbiting the sun. The way that works is that the sun's gravity is pulling it in, and but because I am orbiting, I have centrifugal force, so I am going out. Now all of this becomes a much bigger mess when I now add the Earth. Okay, so moon orbiting the Earth is safe enough. Moon is close to the Earth, or low Earth satellites, Astrosat, International Space Station, close enough that the sun's effect can be kind of neglected. But now, as you start going further away from Earth, you have to worry about the sun's gravity. So I have the Earth here, I have the sun here, and I have some particle in between. What should it do? It has the sun's gravity going this way, it has the Earth's gravity going this way. If it is moving, there's a centrifugal force from that. All of those forces have to balance out. So you can take this entire plane of the orbit. Okay, we are, to make things simple, we are making everything 2D. So there's a single plane, there's the sun at the center, Earth is orbiting in that plane, and I'm throwing in a third body in the same plane. So to balance out all of those forces, you can solve the full mathematical thing, and it turns out there are 5 places where that balance works. Okay, so L2 is the point where I have the sun here, I have Earth here, and then over here I have this L2 point. So on this point, if I'm going around the sun like this, centrifugal force is acting outwards, gravity of the sun is acting inwards, gravity of Earth is acting inwards, and at that point these forces completely cancel out. So that is the L2 Lagrangian point. What it means is that if I put something there and I give it the same orbital period around the sun as Earth itself, 1 year, then an object can sit there. On the other hand, if I put it at some other arbitrary place with respect to Earth and sun, I would continuously have to keep firing my rockets to keep it in place. That requires a lot of fuel, that severely limits the mission lifetime. Now L2, as it turns out, is not stable. So I don't know Unix background, so I'll not go into too much technical detail here. Everyone in the audience should understand it. What I mean by it not being stable is that suppose I take my hand and I put something on top of my hand over here. I can manage to balance it. Okay, so suppose I take my phone here and I put it, I will be able to manage to balance it, but it is not stable. It will very easily fall on the side. Okay, so this is equilibrium, but it is not stable. On the other hand, if I hold it here, it is not going to fall. So that is a stable equilibrium point. So L2 is unstable, and every now and then JWST will fire its rocket engines for a small amount of time to correct its orbit and keep it in that orbit.
Let us quickly jump to the audience who has raised the hand. I appeal audience to ask the question precisely so that we have a lot of questions to be addressed. Let me start with Aditya Nair. Please, Mr. Aditya Nair, please. You can unmute and.
Good evening, sir. So,
Good evening.
I have one doubt that the propellants and the shields which are used on the Parker Solar Probe and JWST, they would have same like the shields used on the MIF for protecting JWST from the sun's rays, and the Parker Solar Probe, that shield which blocks the sun's plasma to go and break, or we can say melt the other particles, and the propellants and the thrusters are identical in both, or they are different?
Okay, so for Parker Solar Probe, this is unlike Aditya L1. This is something that is going extremely close to the sun. So there we do have a sun shield and the instrument. So if the sun is here, Parker Solar Probe has a shield that is shaped like this, and the instrument actually just pops up over the shield and observes it from there. This shield is made of a very different material. Okay, it has to withstand not just the solar light and heat, but also particles from the sun. So that is made of a different material. For JWST, the shield is much larger and also much lighter, and it has to do a lot better job at keeping away the heat because we want to work at very, very, very low temperatures. So because of that, it has all this 5-layer business where it is reflecting that light away to make it much colder. The propellant and so on is broadly similar, but I don't know the technical details of whether they are exactly identical.
Okay, sir. Thank you, sir.
What is the life of the project?
So James Webb is designed with a 5 to 10 year mission in mind. There's a guaranteed 5-year satellite lifetime. There is enough fuel on board for it to last a bit longer than 10. After that, once all the fuel is used up, it will start drifting away from its stable orbit, and then at some point we will eventually just lose communication with it.
Yeah, but if it drifts, where does it go? Sunwards or earthwards?
It depends on what is the last correction that we can do. So the point is this, right? Again, it is this unstable equilibrium story. If I tip my phone slightly this way, it's going to fall on this side. If I tip it slightly this way, it will fall on this side. So it depends on what the last correction done was and which way the drift begins.
Thank you. Thanks a lot.
Okay. Again, it is Junik. Junik, can you ask your question precisely?
I think we have already answered Junik's question, right, Junik?
Yes, sir. Thank you for the answer. It was very precise. And actually, sir, I have a second question. Am I allowed to?
Sure.
Yeah, please.
Yes, sir. My second question was regarding the giant Magellan telescope. As for the image or from the studies that I have done, I've seen the giant Magellan telescope has circular disc-shaped antennas. Now, whenever we are going on circular or round shapes, each of them has a triangular void in the middle of them. So how is this actually causing, is this actually either it's causing some kind of distortions in the image which is being observed?
It will. For everyone else, when I showed this image of all the large mirrors, I showed that a lot of them are now made of smaller hexagons. Now, small is a relative thing. Each of these hexagons is taller than me. They are all about 6 feet across. The Giant Magellan telescope, one of these large telescope projects, actually is using 7 circular mirrors instead of 7 large hexagons. That has to do with technological possibilities that actually allows them to make their telescope based on technologies which that team is expert in. It will have some slight distortions in the final image, but they are at an acceptably low level.
Okay.
Next question is from Subham. I'm going to read the question from the chat box. Subham Barik, as you're going to observe things in infrared, then we will be able to get the images of those celestial bodies in visible spectrum as Hubble captured.
The answer is no and yes, in many different ways. So Hubble's wavelength is the optical wavelength. The light that you and I see is about 400 nanometers to 700. James Webb does see a small part of it. Its sensitivity begins at 600 nanometers. So it can see red light. But the other part is, remember we talked about redshift, light which left as optical light 5 billion, 10 billion years ago from those early galaxies will now appear as infrared. So while it is observing in infrared, it is observing what used to be optical light when it left that object. So in that sense, we are kind of looking at optical light. That is not always the case. So when we are looking at a nearby exoplanet and studying at 10 microns, redshift is irrelevant there. So at that point, we are looking at light which was infrared. And the reason for doing that in infrared is that is one window which you really can't do from Earth. So going to space is important. There are recent technological advantage developments like adaptive optics, which make it possible to do really good optical work from the ground. And making a telescope work on the ground is far, far cheaper than launching the same telescope in space. So for optical now, ground-based astronomy is what is currently the scenario. It may change if all these satellite mega constellations go up. So there are projections that within the next 10 years, so right now there are a few thousand satellites orbiting Earth, but the projection is that within 10 years, there will be more than 1 lakh satellites orbiting Earth. Okay, so imagine trying to take pictures while there are flies buzzing all around you. You'll always get flies in your images. You won't see what your real thing you are trying to get. So that means that ground-based astronomy is under threat. You should also enjoy looking at the night sky while you can, because soon, the next generation, you'll be telling, oh, when we were kids, we used to actually see stars. These days, you only see hundreds of satellites going above your head. So that may change, and we may again have to go to space for optical astronomy. By the way, this is not a joke. This is a serious, genuine threat. China, for example, has plans to launch about 20,000 satellites. There are American and European companies planning 10,000 each. So this is going to be a huge problem, and we are actually exploring international agreements and even legal measures to see what can be done about this.
Okay. Next question is from Chinmaya. Are there any specific galaxies or stars clusters that JWST will focus on to detect IR from billions of years ago? How sure can we be that it is still detectable and has not died out of so many years?
Okay, so that's two questions, both great questions. First is, how do you choose the targets? So the way the targets are chosen is the time on JWST is divided into three parts. One part is called the guaranteed time. The people who built, the teams who built the telescope, they are given a certain amount of time to study targets that they are interested in. The largest fraction of time is actually reserved for a general observer program. So anyone in the world can actually write in a proposal saying, I want to observe this target for this reason. And that is where you have to calculate and show that here is proof that the target will be detectable by JWST. Here is what I will be able to get by studying that target. Here is how, and when I say I will be able to get, of course, I have to publish my results accessible to everyone. So in short, we are saying here is how humanity will benefit if you let me study this star or this galaxy with James Webb. These proposals are reviewed by very senior panels, and they select the best proposals and award observing time for that. Okay, and then there is a small amount of time that is also reserved for sudden last minute things that come up. It's called director's discretionary time, where again a panel decides. So these observing cycles are 1 year long cycles. So they have already announced what observations. So it will start observations in about 4.5 months from now, and the next year of observing from that has already been allocated. Okay. The other question was, how can we be sure that that light is still detectable? The light is detectable. It is reaching us today, right? So whenever I'm talking about a galaxy that is 10 billion light years away, I'm always talking about it implicitly as how it was 10 billion years ago. So if I say, oh, today I saw a supernova in this galaxy, it doesn't mean that it exploded today. It's long gone. Okay, that supernova exploded a long time ago. So think of it this way. Suppose you are watching a replay of a cricket match. Okay, you get as excited as if it was happening live, or if you are watching this lecture as a recording. To you, it doesn't matter that the lecture was done a month ago, a year ago, whatever. To you, it's happening right now. So that's how we look at it. The galaxy that emitted the light may not be around today, but suppose it emitted that light 10 billion years ago, and then 8 billion years ago the galaxy died. It will be another 2 billion years before we figure out that it died. Okay, galaxies don't die just like that, but just as an example. So what we are caring about is what was happening there. It's just like watching a movie. Hero villain ka jo hona hai ho chuka hai long ago, but for you that fight between the hero and villain is happening right now.
Okay. The next question is from Susant.
Okay.
Hello, sir. My name is Susant from Nasik. My question is, how do scientists calculate predicted life of telescope? What are the parameters they consider for it? The second question is there will be any citizen scientist program to scan the huge data comes from JWST in future to connect people like us with this great project?
Okay, so the first part is that designing something like this is a huge technological design process. Okay, so we did it for Astrosat, Growth India. We are doing it now for Daksha. You have to look at it is not in terms of concept, it is not very different from trying to design the life cycle of, say, a car. Okay, you buy a car, you don't want it to break tomorrow. You want it to work for at least 10 years. Okay. If you are ultra rich, you might change it sooner, but you still want the car to live. Someone else might use it. So what you do is you look at how much wear and tear there will be in parts. Phones, for example, in 2-3 years, your phone's battery becomes useless, right? So the telescope has a battery on board. You see the life of that battery. In space, there are a lot of charged particles, and they can actually damage electronics. It is similar to the kind of dangers of being too close to a nuclear reactor. So you have to take that into account. So you factor in all of these and you see how long will each of these components live. And a lot of this analysis is probabilistic. For example, I mentioned something in passing called micrometeors. There are all these small pebble sized things that are going around in space. They are few enough that the chance of any of them hitting a given object is very low, but it still might. So you try to design such that a single chance hit will not destroy everything. To give you a different context for this, this is a big problem for, say, the International Space Station. Okay, a ball bearing size thing, if it hits the space station, actually has enough energy to go all the way through the space station. So there's special thing very similar to bulletproof armor that has been designed to stop that. The chances of that happening are very low, but space station has been up for years and years, so it has happened a few times. Okay. The second question was about citizen science projects. There might be. It's too early to say. What happens is that not all data is amenable to citizen science projects. Okay. So to put it another way, there are some recipes that only the expert chefs in my house can make, and then there is Maggie, which I can also make. Okay, so there are some analysis of James Webb data that only real experts can use to make sense of that. That doesn't prevent you from doing it, right? If you're a student right now, if you're interested in this, you might be a scientist who actually proposes to use James Webb Space Telescope. Today morning, for instance, there was another talk on JWST TIFR's Chand Y, which was given by a PhD student in TIFR. He has 2 approved proposals in the first year of James Webb Space Telescope. So this is not as far-fetched a dream as you might think. You could be one who is using it as a scientist. Eventually, when there is enough data from it, someone may come up with a citizen science project where you normal non-experts may be able to do something with that data as well.
Let us jump to the participant direct questions. Let me ask Hari Shankar Tiwari. Please unmute.
Yes, thank you, sir, for giving me opportunity. Sir, is JWST will see the first photon of the universe?
It will come quite close. Okay, it will be hard to define the first photon of the universe. Okay, and the real story of the real first photon of the universe is actually very sad. It got absorbed long time ago. Okay, so there is something called reionization of the universe, which happens at a very early stage, recombination and reionization and so on. So let me try to keep this brief. Very early on, the universe was extremely hot and dense. If you watch Big Bang Theory, you will remember it as the whole universe was a hot dense soup. That's quite true. What it means is that any photons which were generated there traveled a very short distance and got absorbed. Okay, so why am I saying kind of yes? Around a certain time, the universe started becoming transparent to radiation. Okay, one of those things we see is photons coming from, say, the earliest galaxies. And James Webb will be able to see photons from galaxies which were formed when the universe was just about few 100 million years old, as opposed to the current 13.8 billion years. So in that sense, yes, it will come close, but there is no single the first photon which is still alive. All the first photons are gone. In fact, it is very likely that all the first stars, so we have not yet conclusively detected the first stars. Okay, the naming is funny. There are population 1, 2, and 3 stars. You would expect population 3 to be the newest, but pop 3 is actually the oldest population of stars. And it is expected that they could be very large stars and they'll be almost completely pure hydrogen stars. And we have not conclusively detected any of them so far. It may happen that James Webb may see some of them. Who knows?
Next, Mr. Rohit Chaudhary. Please unmute and ask your question.
Hello, sir. First of all, I would like to congratulate to you, sir. You have a very wonderful style of presenting a lecture.
Thank you.
Yeah, my question is about the point L2. So how does the telescope manages to revolve around the point, since there is no mass, so there would be no centripetal force. So does that
That
mean
is an
it,
interesting question. So
Yeah,
let me see how to.
so does that mean
Mhm.
it is continuously using its thrusters,
No,
or
it's
is there
not.
a stable orbit more than a point? Is there a stable orbit more to call
Okay.
more than a point?
So let me answer this in a slightly technical way first, and I've actually been thinking of this for 2 days, trying to come up with a good analogy. I don't have one yet. Okay, so the technical answer is that if you map the local potential, then all the local potential gradients actually point towards L2. Okay, that's the technical answer for it. Or in the same jargon, this is actually a saddle point rather than a minima, which is why it is an unstable thing along a certain dimension, but is stable along other dimensions. Okay, so let me now try to explain it in simpler language. Remember when I was talking about Lagrange points, I said everything is in a plane. So the Earth's orbit is defining a plane, and L2 is moving with the Earth in the same orbit. So if James Webb moves this way or this way in that orbit, towards or away from the Earth or the Sun, that is not stable. It will start, if it falls this way, it will keep falling towards the Earth. It won't come and hit Earth, by the way. That's no chance of that. Even the slightest side velocity, which it always has, will make it miss Earth. If it goes that way, it will drift into space. But in this direction, it is actually stable. So if it moves up slightly, it will come down. If it moves this way slightly, it will come back. Okay, which means that an orbit like this can be almost stable. It is not fully stable still for a couple of reasons. The main reason there is that we have this giant sun shield that we have put. Sunlight is constantly impinging on that. Now, what we never think about is that light actually exerts force. The force exerted by all this, even on the hottest day on Earth, the force exerted by the sun on us is very, very small as compared to the other forces that we experience. Okay, so for example, the air is constantly exerting a force on us. Okay, there is one atmospheric pressure that is constantly acting on our body. Our body has an area of almost 2 square meters. So from that, you can calculate the force that is acting on the net human body is actually quite high. You can feel the force better if you are in a swimming pool. Your body gets squished. Okay, as compared to all this, that force is very small, so it doesn't matter. But now when you have something that is as large as 1500 square feet, that size, and there is no air, no other major forces acting on it, then and over years and years, that force actually adds up. So it is constantly pushing JWST further and further away from the sun. So, and then it can induce torques. That's why there's a momentum balancing mirror. And to compensate some of these things, every few weeks, JWST will have to fire thrusters for a short amount of time to bring it back close to that orbit. So, unfortunately, this is a simply worded question about a very technical matter. So, I'm afraid I can't make it simpler. Hopefully, it does answer your query, though.
Okay, we'll get back to the chat box. Before that, I have one more announcement. I asked the audience to fill up the feedback form because it will help us to improve our programs. Please, I have already provided the link for the program. Please click the link and fill up the details. Thank you very much. Let me read the question of Caleb. Is the trajectory and motion of JWST audio piloted in case there is any sudden threat of collision or impact from any asteroid in space? The second question, given that we have sent Voyager far enough, is it possible to place an IR space telescope on a stable point along with the orbit of Pluto in order to get farther range of view and also from the sun?
Okay, so let's look at it step by step. The orbit correction commands are given from the ground. The probability of a large enough asteroid hitting it that it will drastically affect the orbit is very, very small. Even if something like that does happen, okay, realistically speaking, if an asteroid large enough to affect the orbit hits JWST, we probably don't have to worry about the orbit anymore. The telescope will be gone. Okay. Um, very, very unlikely that that will happen. Micrometeorite impacts do happen. For example, in astrosat, in a very short time frame, we actually, two of the telescopes on astrosat have gas in them. They are called proportional counters, and two of them lost pressure in a very similar time window. So we suspect that that was probably a micrometeorite impact that actually punctured the telescope and caused all the gas to leak out. So such things can happen. If there are any orbital commands that are to be sent, they are sent from the ground. It is not autonomous. Second is that could we have sent it farther out? Yes, we could. Voyager took decades to get where it is. So we would launch a telescope now and it would take forever to get there. If you can, so think of it this way, okay? If you can accomplish something closer to Earth, then why bother sending it far away? So all the science goals were met. We had to design these very smart sun shields and everything in order to get it to the operating temperatures that we want. And that has worked. And we don't know how well advanced we might be. So there is a capability built into JWST that in the future there could be a possibility that an autonomous mission can go latch onto it and try to bring it back. Overall, the consideration has been that it is going to be technically infeasible to do that because there's no way to fold it back again. And when you start bringing it close to Earth, what happens is if you're orbiting Earth, then occasionally you'll be between Earth and Sun, which means that you are going to be seeing all of Earth's heat from one side, and that can damage the instrument. So there's unlikely as of now, but you never know. In 10 years, the space race might move things forward so much that we might have astronauts capable of going to L2 and doing repairs there. That is also a possibility. But sending things further away is far more expensive. So you don't do it if you don't need to.
The next question is from Chitraleka. Sir, extraterrestrial intelligence are possible or not? What about UFO and how the James Webb Telescope will study this?
All right, so let's break it down into step by step. First is that there is a huge gap between dead and alive. Right, we have found a lot of planets. We don't know if any of them have any form of life. And by life there, we are usually talking about unicellular organisms, algae probably. Okay. Then there is another big jump to go from unicellular to multicellular life. From that, so there we are talking about, at least coming up with plants. From there, you are talking about intelligent life. And intelligence also, dolphins are intelligent, but they don't build rockets. From there, you have to go another stage to become a civilization. Okay, so when we are talking about aliens, we are implicitly talking of that stage. But if and when we discover life elsewhere in the universe, it will more likely be somewhere much lower down this ladder in the form of vegetation or something like that. Okay, UFOs, there is zero credible evidence that aliens have visited Earth. I would love it. I watch all these sci-fi movies with aliens and so on. I would love it. Okay. But as a scientist, what I want is different from what I know is there. And there is evidence, unfortunately, so far that there are any UFOs that are zooming around. I will give you a very simple reason and argument for that. Okay. Suppose you take extreme, imagine that there's a tribe of some different species living on Mount Everest, okay, on the top of Mount Everest. So you have to put in a lot of effort to just go there, right? You have to first become a mountaineer, you have to then hike all the way up, go to the summit. After going there, would you not just go out there and say hi? I mean, you might first observe them to decide if they're safe to visit or not. But given that you have the technology of going all the way there, you are not going to be seen only as blurred photographs of weird discs or whatever. Okay, so these are all theories, conspiracy theories. They are not even theories; they are hypotheses. Really, the word conspiracy theory itself is misleading. They are all random hypotheses that come up. We would love to have aliens and UFOs. Unfortunately, just given what we understand about the physics of the universe, it is extremely unlikely that they will visit us. And it is extremely unlikely that based on whatever evidence we have so far that any of them actually have come to us.
The next question is from Harshvardhan. Instead of making,
I think he also has his hand up, right?
Right, yeah. let us go for his text. Instead of making different telescope for each of the wavelengths, like one telescope for IR and separate one for visible and another for microwave, why can't we make one telescope with the ability of for all wavelengths? That's the
That is a great question, and the answer goes back to physics of optics and physics of detection and so on. Okay, for example, if you want to look at stars, you get a normal optical telescope. Okay, but if you want to watch dish TV at home, you don't use an optical telescope. You are the radio waves coming to you are also light, but you don't put a lens to gather that. You put a small dish outside your house. The reason for that is the way light interacts with your lenses and mirrors and everything is different for different wavelengths. Okay, X-rays go through everything. Radio waves also go through a lot of stuff or get completely blocked. So based on the wavelength of light, if you want to focus that to get light into to get sharper images and so on, you can't use the same material. Normal telescope mirrors that you'll see are silver. JWST mirrors, as I said, are coated with gold. Very tiny amount of gold. That layer is some 700 atoms thick or something like that. Very thin layers. Okay, but even to do all of that, you need a special material for each wavelength, and then you shine that onto a camera. The camera has to be able to see that light. So your normal telephone camera, cell phone cameras, for example, work in optical and near infrared. You need silicon-based detectors can only work in those regimes. Some different detectors are used in soft X-rays, hard X-rays. Yet other types are used for radio waves. Antennas are used in radio. So we haven't yet discovered a material that can reflect or bend either way all wavelengths of light, and we haven't yet discovered a material that will be able to detect all forms of light. So that is what prevents us from doing that. Also, requirements are very different. Optical telescope can be few centimeters to tens of meters, but if you look at GMRT, for example, India's giant meter wave radio telescope, those dishes are 45 meters in diameter. There's no optical telescope of that size. The largest radio telescope is actually 0.5 kilometer across. It's called FAST. It's a instrument in China. Because radio waves are that much weaker, you need much larger telescopes to get them.
Yes, sir. But the larger aperture, is it for better resolution or collecting more light?
Both.
Okay, sir. Thank you, sir. My question actually was that not about why don't we use normal optical telescope for seeing radio waves. My question was exactly that why can't, even if we have to use all different instruments like a radio telescope, a microwave telescope for seeing all these, so why still can't we send all of them at once? But thank you, sir, you have answered that that it's they are specialized instrument for all of them, so we can't send them all at once. Thank you, sir.
Okay, we have a lot of questions. I think I would like to read a couple of questions and we'll close it. And what my suggestion is, let me send the questions to you. Again, we have a lot of instruments to communicate to our participant. We have the Google group and we have the Telegram, we have WhatsApp, many things are there. So we will answer all the questions from, answer questions after I get the answer from you. That way we can move. Okay. The next question is Harishankar Nath. Our universe is expanding. How can we see the birth of the universe?
That is a very interesting question, and it's actually deeper than what you might think about. The universe, how do we see the birth? Well, the short answer is if the universe is expanding at a speed slower than the speed of light, then at some point you'll see the end of the universe, which is really the birth of the universe. Turns out that the universe is currently expanding slower than the speed of light, but at the birth of the universe, it very likely went through a phase called inflation. And what that means is that at that point, light traveled, the universe grew so fast, we don't even know how much it actually grew during inflation. Okay, there's a lot of uncertainty around all of that, which means that we don't know how long ago this was. How long ago is also in a very technical sense here. we don't know how far away that point, the initial point was. Another question one might ask is in which direction is it? It's in all directions. All of this stuff was squished in at one point. Okay, so think of it. Let me give you an example. Okay, suppose there's a large crowd standing on an open ground. Okay, and everyone is standing very close to each other. Okay, what you have to do, the outer ring is consisting of players who are going to start running away. Okay, and to see a player, you have to go and stand next to them. You have to catch them. Okay, so suppose the outer players are running extremely fast and you start, say, 10 minutes or 10 seconds later, you'll never catch up with them. If the outer ring is all Usain Bolts, you are gone. On the other hand, if the outer ring of these people running away is people like you and me, and Olympic sprinters are standing in the center, then at some point they will catch up. Okay, which direction they run in to catch up doesn't matter anymore at that point, because it's all a ring. Everything was at one point initially. Okay, so in case of our universe, it turns out that initially the edge or all of the universe expanded very, very fast. So there are currently, these are, you can think of them as connected bubbles as such. For every point in the universe, there's a sphere around it up to which that person has seen things. There's another sphere here, there's another sphere here. There are some spheres which have intersected, others have not. We don't know how far away the edge would be. We don't have full understanding of that yet.
So next question is, Sarika, if multiple telescopes orbit L2, how does JWST avoid capturing the heat produced by these telescopes?
That's a great question. Good, you thought about it. The orbit around L2 is something like 1.5 million kilometers, if I remember it correctly. I might be mixing up a number here, but we are talking about a 1 million kilometer orbit. Okay, so it is extremely uncrowded there. So the distance between these is millions of kilometers, so their heat is negligibly small. Okay, they are all very cold as well.
Yeah, okay. Well, this is the last question from Sandeep Batula. Can you throw some light on what one can expect by looking at the TRAPPIST planetary system through JWST?
Okay, so TRAPPIST is a survey that was done. They've studied many stars and found planets around many of them. You're probably referring to one of the systems discovered by the TRAPPIST survey are called TRAPPIST something. You're probably talking of one of them. My own area of work is not exoplanets, so I'm not sure which system you might be talking about and what JWST might do about it. So if Sandeep is here, maybe he can unmute and ask.
Yes, sir. Good evening.
Yeah.
Yeah.
It was a great session to end our weekend. So my intention was it's about TRAPPIST 1A, and recently we have found that the TRAPPIST 1A planet was in a Goldilocks zone, and it is tidally locked to its parent star. So and it was expected that there would be a chance of finding the life on this planet. So would there be a chance with JWST?
Okay, so I don't know. So there are few hundred approved programs with JWST. I don't know if TRAPPIST 1A is one of them. I would like to caution a bit about chance of finding life. This is something where popular representations can misrepresent what astronauts are thinking about it. So what astrophysicists are thinking about. Sorry. When we say chance of finding life, it means that we cannot guarantee that all life will be dead. All right. So if you have something which is called a hot Jupiter, if you look at something like Mercury, we say no chance of finding life. It means that place is cooked. There is no chance of finding life. Okay. So when we say there is a chance of finding life, it means that if we were to go and set up, we could possibly set up a viable system there. That does not necessarily mean that even unicellular life has evolved and so on, and then going through all those stages through intelligent life. That's a far stretch. Yes, that with that caveat, there is a chance there. Unfortunately, I'm not aware if there are exact plans of JWST observations of that. The JWST observing schedule is publicly known, by the way. So if you go to the For Scientists page, you will get a list of all the approved proposals and everything. So you will be able to find out whether JWST is studying that particular system.
Thank you. So we have exceeded 7 minutes now. Unfortunately, we have 1 hour question answer session, more than 1 hour. Unfortunately, we are not able to cover up all the questions. Anyway, we have other opportunity to cover that. Thank you very much. Now I invite Mr. Sellakumar to give the vote of thanks.
Good evening, everyone. On behalf of the Popular Science Lecture of Tamilnadu Science Forum, I extend my thanks to our respected speaker, Dr. Varun Balerao, to take out time from his busy schedule to grace the event. Thank you, sir. Thank you for your excellent and interesting lecture about the JWST, its engineering marvelous and scope of the projects. A special thank to Dr. T.R. Govindarajan and Dr. R. Ramanujam for providing immense support to make the webinar successful. I extend my thanks to Mr. Vijayan and Mr. Sundar and all my colleagues in the PSL Executive Committee to organize this webinar successful. I must thank to the audience for listening the webinar and their cooperation. Thank you everyone once again for making it the program great success. Have a great weekend. Vanakkam நண்பர்களே.
Thank you. Thank you, Varun. It's a great talk. Thank you very much.
Welcome. Thanks, everyone. Have a great day.
Thank you, Varun. Great hearing. I was listening.
Yeah.
Thank you.
Okay. Thank you.